Good morning to everyone, and thanks so much for joining us this morning. I am Agnaldo de Souza. I am from CINE, the Center for Innovation on New Energies. I'm talking from Campinas right now, and we have some audience right here. Thank you so much for joining us. And don't forget, please, to ask your questions at the end. And please, don't forget to subscribe to our channel if you think it is worth. And also, don't forget to hit the notification button so you don't miss any of our events. Today, we're going to have the third webinar of the year, and we are quite honored to have this special guest. And thank you so much, Professor Claudia Longo, who invited Professor Chris to contribute to our events today. It's such a very interesting subject. Thank you so much for the contribution, Professor.
Okay, good morning. So I'm really glad to introduce you, Professor Chris Hardacre, our collaborator in the Dense Energy Carriers Division at CINE. And thus, Professor Chris is vice dean in the University of Manchester, and he's visiting Brazil, sponsored by CINE. And tonight, we are going to the meeting of the Brazilian Society of Chemistry. So Professor Chris arrived and visited the Unicamp yesterday. So I'm really pleased to introduce you, Professor Chris. Professor Hardacre, he obtained his PhD in the University of Cambridge in 1994, and he's working in the University of Manchester from 2019. And he also works in the Photon Science Institute, the Dalton Nuclear Institute, and the Manchester Environmental Research Institute. And he is vice dean and the head of the School of the Natural Sciences at the University of Manchester. So, Professor, please give us your talk today. So I'm very pleased to have you with us.
Thank you very much indeed, Claudia. It's a great pleasure to be back in Brazil. It's 10 years ago since I was been in Brazil before, and I've collaborated with Claudia ever since I was here then. And I'm going to talk a bit about some electrochemistry work that we've been doing, as well as some CO2 capture work, and also to talk a little bit about perhaps a new method to understand electrochemical processes. Oh, what am I doing? Okay, so as I say, I'm going to talk a little bit about CO2 capture in ionic liquids, first of all, and then how we might be able to convert that CO2 using electrochemical means. And then I'm going to talk, if I have time at the end, about modulation excitation to probe those electrochemical reactions. So why are we interested in CO2 capture? Well, of course, we produce a lot of CO2 from fossil fuel derived materials, and obviously the issue to do with global warming and the increasing amounts of CO2 in the atmosphere, we've got to get rid of it in some way. There are a variety of ways of doing that CO2 capture. You can put it in deep saline aquifers, for example. You can use it for enhanced oil recovery, or you could combine it with solid materials like calcium oxide to form calcium carbonate. Obviously, a better way to do it is to not use fossil fuels and do the natural carbon cycle. And you can see the natural carbon cycle here, where you're capturing the CO2 from the atmosphere using photosynthesis. You then are going to use that biomass to produce chemicals and so on. And then you go around that loop without necessarily needing to go via the fossil fuels. But of course, we can use that CO2 rather than just store it. And we can take that CO2 that we capture, we can generate hydrogen. You generally need a reductant, of course, with CO2. You can generate that hydrogen that you require either via electrolysis, and you can make things like methanol, you can make synthetic hydrocarbons and fuels, and then take it back ground through atmospheric CO2, and that's a renewable source of carbon then. So this is the types of things that you can do with carbon dioxide. And of course, just recently we had the issue to do with the energy crisis and the oil going up in price. And certainly in the UK, fertilizer factories, for example, were closing down, which was causing us a real problem because they produce CO2, and that CO2 is used in a wide variety of commodity commodity products, including things like food and health. And so there was a big crisis in the UK about how were we going to ensure that our food supply and our health supply was going to be maintained. For the purpose of this presentation, though, what we're interested in is the stuff in the red box here. So making things like methanol, liquid fuels, and secondary chemicals from the captured CO2. But of course, you do have to capture it to start with. And there are a variety of ways of capturing the CO2. The current technology is using aqueous monoethanolamine, MEA, and it's very good.
Chris, just sorry to disturb you, but we need to put the slide in the presentation mode because the slide is not running. You should put in presentation mode.
I was in presentation mode, so I don't.
No, was not. We should put it in presentation mode, otherwise it's not going to run it.
Okay, I did have it in presentation mode, so I'm
but
not quite
for
sure.
us was not. Marcelo, if you could just get in and just try to help. Marcelo, please.
Yes. Yes.
Is that in presentation mode?
Not yet.
Not now.
Oh.
Maybe stopping the sharing and start sharing the entire screen and not the window.
Okay, I can do that. Let me do that. Apologies.
No problem. Don't worry. We are sorry for that because we should be make everything to be right.
So share screen.
Share the entire screen.
Entire screen. Okay. Yep. So share. Oh, it doesn't allow me to do the share window. Share. Can you see that now?
Now you can put in presentation mode.
Does that work?
Not yet.
Not yet.
No?
No. You need to choose to share the entire screen and not the window.
Yeah, it wasn't allowing me to do that, though. So share. So share screen. So let me try that. Can you see that now?
Yes, now it's gone. Okay, thank you very much.
Okay. Great.
All right.
You can rewind some slides.
No, we are sorry for outside. Thanks.
Thank you.
Okay, so as I mentioned before, this is the cycle that we'd like to be able to do: capture the CO2, convert it using hydrogen from things like electrolysis to make fuels and so on. And so we can see the types of things that you can use that CO2 for in this slide. And the interesting part for us is in the red box on the right-hand side. So the current technology, as I mentioned earlier, is aqueous monoethanolamine. And you can see the molecule here, and it's very good. It's got high reactivity. It absorbs a lot of CO2, 1 mole of CO2 for every 2 moles of MEA, and it's low cost. The difficulty, however, we've got with it is that we lose amine, so there was a contamination of the environment. To regenerate that MEA, it requires lots of energy, and so are you gaining much in terms of the CO2 that you capture? And it's also very corrosive. So what we've been interested in is whether ionic liquids could be a possible replacement for that MEA. Just to give you a reminder about what an ionic liquid is, I'm sure that you all know, but just to give you a reminder, these are liquids which are only made up of ions but have low melting points, so they don't melt at 700 Celsius, they may melt at room temperature, for example. And we do that by making the ions bulky, asymmetric, so they don't pack very well, and you can delocalize the charge, and so you don't have a point charge, and so therefore you reduce down your Coulombic interactions. And you can see a version here where we've this is an Imidazolium-based ionic liquid where we have distributed the charge around the ring. We've also distributed the charge in the hexafluorophosphate around the phosphorus atoms, for example, and that they're big bulky ions, for example, they don't get too close, and therefore this one melts at low temperature and certainly below room temperature. You can obviously change the cations and the anions, and that changes the physicochemical properties, the viscosity, density, heat capacity, and so on of that ionic liquid. So we've been looking at these for CO2 capture, and those physically absorbing ionic liquids, the things like the Beam PF6, which I've just mentioned, they don't have great CO2 solubility compared with MEA, better than organic solvents, but still only sort of 0.04 moles of CO2 per mole of ionic liquid. And those were reported back in 1999. People have also tried to mimic the MEA by making amino acid-based ionic liquids, and you can see those types of systems in the right-hand side. And they absorb lots of CO2, as you would expect, but they also have a large increase in the viscosity when you absorb the CO2. So they're not great in terms of process engineering. In 2010 or so, some super base ionic liquids, which were made by deprotonating an amine, as you can see at the bottom here, you can see the triazolide-based systems, they will absorb CO2. And they have equimolar CO2 uptake. They're recyclable. You can do pressure swing or temperature swing absorption and desorption, as you can see on the right-hand side, and you can recycle them over a significant number of cycles, in this case 25. And there's very little change in the viscosity, only a small increase. So we were interested in those materials and trying to understand them. In particular, of course, you don't have pure CO2 in most cases. You have impurities. It could be water, it could be things like H2S or NOx or SOx. And so we decided to have a look at a range of these superbase ionic liquids in the presence of impurities. First thing to note is that they do work under wet and dry conditions. You can see here a whole series of dry ionic liquids in the first column and the wet ionic liquids in the second column. And you can see there's some differences between the two, but they all work. And in particular, the benzimidazole system is very high in terms of its CO2. We can also get an enhancement of the CO2 absorption with water, which is perhaps a little strange, but it also can have a negative effect as well. You can see the negative effect happening with the benzimidazole and the positive effect happening with triazolide-based ionic liquid. We've looked at phosphonium versus ammonium-based ionic liquids, and the reason for choosing the phosphonium and ammonium-based ionic liquids is that they're cheap. They're also hydrophobic, so they will not dissolve in water, and so the effect of the water can be quite limited. And there's a lot of water around in these cases. You can see, however, that the phosphonium-based ionic liquids and the ammonium-based ionic liquids do both absorb the CO2, but what we can see is we can see an actual increase in some of the. I do apologize for the background noise. I'm sitting in the corridor because the internet is better out here. You can see that you can enhance the CO2 absorption with the ammonium-based ionic liquids. However, they are cheaper slightly than the phosphonium-based systems. However, they are also a little bit more unstable thermally, and so we prefer overall to use phosphorus-based ionic liquids, the phosphonium systems. Those ionic liquids are nice and recyclable. This is dry conditions. You can see 6 cycles of these. We can go up to 30 cycles. That's what we've done. Under wet conditions, we also get very good recyclability, and the addition of water has very little effect in terms of the irreversible effects on the ionic liquid uptake of CO2. What is actually happening when the ionic liquids absorb the CO2 is you form carbamate in general, we think. And you can see the carbamate being formed here. The NMR data indicates that. And it doesn't matter whether you're under wet or dry conditions, you still see this feature at about 160 ppm. We can see that occurring in the NMR here, and you can correlate the size of that NMR peak at about 160 ppm with the uptake values that we get from gravimetric data, which is of course what you'd expect. More interestingly, I think perhaps is what is happening around the cation. So what is the effect of the cation? We can see this feature sitting around about 2 ppm, and this is associated with the CH2s that are right next door to the phosphorus. And you can see that they move depending on whether or not you have wet or dry conditions, which sort of indicates that actually those CH2s are interacting quite strongly with the anion. And we get some interactions both to higher ppm as well as to lower ppm. We've done some calculations to understand what the structures of those materials are, and you can see here some DFT calculations on the interaction of the anion, as you can see with the blue, interacting with the phosphorus, and in particular with those acidic CH2 groups. And you can see that when you have CO2 adsorbed, which binds to the anion, those also interact with the CH2 groups as well. The shift that you see under wet and dry conditions suggests that the CO2 competes pretty effectively with water. So the reprotonation of the anion, the CO2 can prevent that from happening to some extent. Now, of course, when we look at the water absorption, we can just do it gravimetrically. The water doesn't go away too much. However, when you're looking at other gases like SO2 or NOx or whatever, you're going to be wanting to look at both the CO2 absorption as well as the impurity. And so we developed a mixed gas absorption setup, as you can see on the left-hand side here, where we have our feed. And the key thing is that we have the gas out going to a mass spectrometer. This is more akin to what we would normally do with our heterogeneous catalysis work. And you can see a typical mass spectrometer profile. You can see the uptake as a function of time. We have a tracer in there, and you monitor the difference, which is the bit in green, between the tracer and the breakthrough. We can also then switch it from absorption mode to desorption mode, where we just desorb in argon as a function of temperature, for example, and we'll see the desorption peak. And we can correlate the desorption peak with the amount of absorption as well. And so we can monitor using the mass spectrometer. The mass is associated with CO2, for example, as well as SO2. So this gives you some real data on CO2 and SO2 absorption. We've reduced down our CO2 down to 14% in argon. This is with the phosphonium benzimidazole system, and about 2000 ppm of SO2, which is quite high for these systems. In the first cycle, you can see in blue the CO2 absorption, and you can see this, if you had a tracer, it would go up and then straight across, and you can see you've got an absorption area here, as well as the desorption of the CO2 as you increase the temperature. You can see, however, the time that we've got here, it's over 100 minutes for absorption, so it's pretty slow uptake kinetics, which is not surprising given the viscosity of that ionic liquid. You can also see that there is no breakthrough or desorption of SO2. In other words, all of the SO2 is absorbed, and it doesn't break and it doesn't desorb either. By the time we've done 8 cycles, though, we've got a reduction in the amount of CO2 that's absorbed. The area over here has decreased compared with here. You see that the desorption peak that's highlighted in the red circle is also much smaller than the upper curve. But you can also start to see some desorption of the SO2. So that only occurs after multiple cycles. And you can see that here. This is the uptake values of CO2 in the presence of SO2 in the purple bars, and the green line is the 14% CO2 only without any SO2 there. We can see that actually what you get is you get just complete absorption of SO2, and gradually it just accumulates in the ionic liquid. But there is a reduction in the amount of CO2 that you can absorb in the presence of SO2, and then it starts to gradually go down as you increase the number of cycles. The accumulation of SO2 in those ionic liquids is shown here in the XPS. You can see that we see some of this SO2 binding to the anion, but we also see after a large number of cycles some reduction of the SO2 into sulfur zero. We haven't probed this too much, but we have got some clearer change in the SO2 oxidation state. So let's have a think about whether or not you can get competition between the SO2 and the CO2. So we've looked at using infrared spectroscopy, in particular using attenuated total reflection to characterize the SO2 and the CO2 bands. And what we see is, you'll see this in a second, what we see is the CO2 binding to the benzimidazole, for example, like this. The SO2 binds as well, and you can see the characteristic bands. But actually, the infrared shows that when you've got this CO2 bound and you put in SO2, you displace the CO2. We've also looked at NOx, so that's another gas as an impurity in the flue gas. And what we see is we see that we can absorb lots of NO2. But we don't absorb huge amounts of we absorb some NO, but we can absorb, as we do with SO2 rather, we can absorb lots and lots of NO2. Now the question is, how is the NO absorbed? We don't really we didn't know at this point, but I can give you some identification of that in a second. What's the effect on the CO2? You can see that here. So we've already seen the work on the SO2, which is shown in the triangles. We see this large decrease in the CO2 absorption because of the irreversible absorption of SO2. The NO2 will also cause a large decrease in the CO2 absorption, as you can see here. It's not quite as bad as the SO2 effect, but it is significant. Whereas in the case of NO, although you can absorb the NO quite significantly, you don't really see a change in the CO2 absorption. And that's shown here for the 1,2,4-triazolide system. We can see that we can decrease significantly the NO2 effect if we change the anion of the ionic liquid, as you can see here. If I go back to this point, this is for the benzimidazole system. You're seeing a large decrease in the CO2 absorption for the NO2, whereas when we change it to the 1,2,4-triazolide, we can reduce that effect down significantly, as well as reducing down the effect of SO2 as well. The XPS gives us some good information about both NO and NO2 absorption. You can see here the blank on the bottom without anything absorbed. As soon as we absorb the NO, we see this additional feature in the XPS at 402.4 EV. And we think that this is associated with this no-no species, so this dimer of NO, as opposed to this one here. You'll see some density functional theory calculations of that in a second. In the case of the XPS of the NO2 absorption, you can see 406.1 feature appearing, and we think that's the NO binding like this. So we can look at the ATR as we've shown before, and what we see is these bands appearing which indicate that we do have this no-no species. We can also see some additional bands where we can get the no-no species on both of the 2 nitrogen in the benzimidazole system. When we have the co-feed of NO and CO2, we see both the CO2 bands in green as well as the no-no species. And the fact that we have 2 nitrogens shows you why the NO does not compete with the CO2 binding. Let's have a look at the density functional theory. What we can see is the binding strengths here of various species on the benzimidazole. The SO2 binds extremely strongly, minus 29.6 kilocalories per mole. CO2 also binds strongly, minus 13. NO2 binds strongly at minus 8. And the NO, if it's just NO, doesn't bind very strongly at all. However, if we start to look at the no-no species, the one that I spoke to you about a moment ago, you can see it does bind very strongly, and you can bind 2 of them, but the binding strength of 2 of them is smaller than the binding strength of CO2. So it will, one of the CO2s will displace one of the no-no species. And so we think we understand now how both NO, NO2 and SO2 bind to the system. Now, of course, we'd like to have a whole process. We'd like to be able to use an ionic liquid overall in a process. And so we've looked at 2 different ionic liquids, benzimidazole, which I've talked to you about a lot already, as well as the tetrazolide-based system, which you can see on the right-hand side here. Interestingly, if you look here, it doesn't bind CO2 very well, but it does bind SO2 extremely well. And so we can use this to separate the SO2 and the CO2 from each other. It's also the case that the SO2 binds much more weakly with the TETs-based ionic liquid than the benzimidazole. And so you can actually regenerate the TETs-based ionic liquid with from the SO2. This is what we have. We have a 2-column system, one with the TETs that you feed first. You then remove the SO2, and then you can capture the CO2. And that gives you a way of separating the CO2 and the SO2. The SO2 you could then use for things like sulfuric acid. This gives you some idea. So the gray line is what happens when you just have the benzimidazole, which is what I've shown you already. You get a very large decrease in the CO2 uptake. The open bars are what happens when you have the TETs followed by the benzimidazole. And what you then see is you see a much more decreased loss of CO2 absorption as a function of cycle. And you can see it actually levels out over here. There's a small amount of SO2 that gets fed through from the TETs. If you had a larger column of TETs, then you would take out all the SO2, and that would increase the CO2 uptake in the benzimidazole system. We've done some Aspen modeling of this as well to give you some idea about how we can do that. Again, we have the TETs coming in here. We then separate out the TETs-based ionic liquid from the SO2. We can regenerate that TETs-based ionic liquid and recycle it, of course, and capture and use the captured SO2. We can then put the CO2 that's coming through from the TETs-based ionic liquid into the benzimidazole, desorb the CO2, and then recycle the ionic liquid. And this works pretty well. So overall, we understand now CO2, SO2, NO, and so on uptake in the ionic liquids, and also how we might be able to utilize the ionic liquids for an overall process. But of course, we'd like to be able to use that CO2 in a reaction. The problem that we've got, of course, with CO2 is that the CO2 is the thermodynamic sink for carbon, And so we need to activate it. And the way we can activate it is by adding an electron, forming the radical anion. We have seen in the literature there can be a reduction in the overpotential for that when you have the ionic liquid there. But the focus at that point had been mainly associated with physically absorbing or low capacity CO2 absorbing ionic liquids. So again, we were interested in using the chemically absorbing ionic liquids, in particular this CO2 in the superbase systems. And here's some initial data on the cyclic voltammetry. You can see here in the red the ionic liquid just in acetonitrile. You can see here in the blue what happens when you add a bit of water. You then reduce down the overall reduction window. You can see what happens when you just have the CO2 there in the ionic liquid. You see, again, a reduction in the electrochemical window, but not too much more. But however, when you have water and CO2, you see this feature sitting around about minus 0.7 volts. And this is associated with the reduction of the CO2. So you require the water and the CO2 there for the low overpotential reduction process, which is right because you need to generate protons. Now, is it something to do with the chemically absorbing system? Well, we think it is. If you look at a physically absorbing system, in this case, the bistrophlamide-based system, you can see that you don't really get that feature occurring that we just saw a moment ago. And you can see here the big difference in the CO2 capacity. So, of course, we need to check what we were forming. So we have an electrochemical setup here where we can both take gas samples via a gas syringe as well as liquid samples via a liquid septum. We've used gold, platinum, and silver as our electrodes. And you can see here that we form formate. And you can see we form a significant amount of formate in the silver-based electrode. We also form some CO and some water. I do apologize. Some CO and some water. But the formate we can form at an applied overpotential of 0.17 volts, which is very low. It's a bit slow. We get very good Faradaic efficiencies, but this, because of the viscosity of the ionic liquid and so on, this was a very slow process. It took half a day or so to form to pass 10 coulombs of charge. You can see here the bistrophlamide versus, so this is the physically absorbing ionic liquid versus the chemically absorbing ionic liquid, and you can see there's a massive difference in the amount of formate. In fact, you don't form really very much formate at all in the physically absorbing system, where you form significant amounts in the chemically absorbing ionic liquid. You do see some CO and some hydrogen, of course, in the bistrophlamide-based ionic liquid, just because of the water and the reduction of CO2 just being in solution. We also see those in the chemically absorbing systems as well. So what is happening? We, of course, need the protons to form formate, and we can also form some CO that way as well. And that's at the low overpotentials. At the much higher overpotentials, the CO2 will reduce on its own. It forms an ion pair with the phosphonium-based system. We can reduce down the CO2 to CO, as well as to form some formate as well. Interestingly, if we use platinum or gold, we can also see some formate as well. But actually, the best system that we've got there is silver. In the case of the platinum, you activate water very significantly, and gold you don't do too much. And you can see those here. You can see the silver-based system at low overpotentials. We're seeing significant amounts of the formate production, as well as on the platinum and the gold. As soon as we go to, but we don't see so much activation of for example, of the system over the platinum. We can also do this with a mixed gas feed, and you can see that here. We've done this with SO2 being present, and we see some quite significant reductions. You can see here's the CV of what happens when you have SO2 being present. And we think that's because you form this S2O4 minus species. We also potentially see this this interesting dimer, and the infrared sort of shows that too. We still see some formate being produced, and you can see that being produced here in the presence of SO2, which is good. So overall, we can form formates using these chemically bound CO2s to the ionic liquid. So overall, we have a process where we can capture CO2. It also gives us a process by which we can capture the hydrogen and store it and utilize it using this sort of cycle. So overall, we've shown that you can reduce the CO2 down. We know the trends associated with SO2, NO2, and NO. We've been able to use infrared and density functional theory to illustrate the competitive absorption of those gases. And the ionic liquid has been shown to be able to do that, except with the SO2 and the NO2. We can tailor it to some extent, but we do have an irreversible effect on the ionic liquid. We can also, of course, convert the CO2. We've also used this ability of the NO2, for example, to bind to ionic liquids to utilize the fact that we can modify things like hydrocarbons so that the NO2 doesn't oxidize the hydrocarbon as well, and that's being investigated further. I just wanted to finish in the last few minutes with some very new data on how we can study some of these electrochemical processes. We've been interested for a while in increasing the sensitivity of some of our processes that we're into, some of our techniques. So for example, EXAFs or neutron scattering. And part of the problem with many of these situations is that you either need an idealized system where you can very effectively see the active sites, or you need to improve the sensitivity of your technique to be able to distinguish between the spectators and the active sites. So when you have a model system, you're over here at number 3. But actually, most of the cases, you also have spectators. And if the spectators and the active sites are in similar quantities, you should be able to see the active sites. But in many cases, the spectator species, the solvent, for example, or a reactant that hasn't reacted, or the product being present or whatever, far outweighs the active sites. And you're in this situation on the left-hand side. How do you distinguish between a very small amount of active site or species and everything else that is not important? So you can use this technique called modulation excitation, and what you do there is you put a sinusoidal stimulation, so you can turn on and off, for example, the reaction, and that stimulation, you can see at the bottom here, gives you then a change in the active species response, and you can see that in the top part of that spectrum. That stimulation could be a change in voltage, it could be light on and off, it could be heat, it could be a change in concentration. And you can see here that the stimulation versus what happens with the active species response is offset in terms of phase. And what we can therefore do is probe this phase delay. And if we do that, what you see is in the time domain, so if you see it in real time, you can see the noise, and you can see that here. You can see the spectator response, which will not change as a function of the stimulation. And you can see the active species response, as you can see here. If we then look in the phase domain, in other words, we're looking at it as a function of the phase, this phi time term, what we then see is that the spectator response is 0. So we will dismiss all of the spectators. The noise response, it will also be 0. And all we will then see is the active species response. So we haven't done it as yet with CO2, but we have done it with a model system, ferrocyanide to ferrocyanide. So in other words, the iron 3 to iron 2 redox couple. And you can see here on the top right-hand corner, the CV, typical CV of a reversible couple. And we're looking at this with X-ray absorption fine structure. This is our setup. These are our cells. We have a reference cell and a sample cell where we have a 3 electrode system. We have our beam here of X-rays that goes through the cell. We monitor the X-ray absorption, and we can then look at the fluorescence. And this is what we see. So this is the XAF spectrum as a function of the voltage that we apply, and we go between, we just basically cycle along this CV. Now this is a set of spectrum that are overlaid. You can just about see, hopefully, the lighter colored lines are behind the purple line. We see the normal absorption, and then we see the fine structure associated with the XAFs as we go past the absorption edge. This is at the iron K edge, and you can't see any change as a function of the CV, so the time of the CV. And that's what you'd perhaps expect. You're probing the bulk liquid. You know, you're not seeing too many species that are being oxidized or reduced. And so this is during a CV. It's not bulk electrolysis. It's in 1 mole of sodium chloride. So if we look at that in a bit more detail, so what we've done is we've extracted the data from past the edge, and we've multiplied it by the wave vector k, and the square of that wave vector, so that we can see the oscillations in a bit more detail. And this is the time resolved spectrum. So this is the same as what we've just seen. It's k squared times the chi data. And you can see just about perhaps a little bit of change as a function of time, but really nothing. However, as soon as we just look at the phase change data, the phase resolved data, you can see that here. And you can now start to see some significant changes as a function of time. And this is really showing you that you can start to probe very, very small amounts of material. And in fact, this is at 30, I think it's 30 millimolar concentration in the bulk solution over here. I reckon we need to do some calculations to look at the sensitivity, but it's at least 1,000 times better sensitivity than what we had over here, if not a little bit more. So we're probing things down at the micromole level now. So can we look at the radial distribution function as a function of the potential? So we're doing our CV here. This is the radial distribution function that we see, and we get that radial distribution function by Fourier transforming this. So we're picking out the various frequency components of the XF's data. And that's what we see here. And these are associated with bond distances. So this first shell that you see, so you're sitting on the iron, we're looking out, and this first shell that we see is that first carbon of the cyanide group. The second shell is a combination between the single scattering of the nitrogen as well as the multiple scattering of the cyanide. And you can see that here. As a function of time, you see some very, very small changes in the amplitude, but nothing too significant in the time resolved data. In the phase resolved data, however, you start to see some really big changes. So this black line is the oxidized species, and the red line is the reduced species, and all of the gray ones in between as a function of the voltage that we've applied. And that's in the oxidative sweep, in the reductive sweep. As we're coming back down here, we're starting to see the reduced species dominating in red, with a bit of the oxidized species appearing. What you notice, however, is you see this large shift in the second radial distribution coordination sphere. And if we look at the reference spectra, we don't see that. So the reference spectra for the reduced species is in black, and for the oxidized species is in red. And you can see the second shell has very similar amplitudes, and also the position of those is very similar. We do start to see some changes in the first shell, as you might expect, and you would see a shift of the overall peak as you go from the oxidized to the reduced. We see that shift here between the black and the red, as you'd expect from the reference spectra, but we do not see the invariant second shell that we see in the reference spectra in our in situ data. We need to do some more analysis of why this is, but we feel that this is something to do with the hydration sphere as we get very close to the electrode surface, because the species that you're seeing here are close to the electrode surface rather than in the bulk system. They haven't had time to diffuse away from the electrode potentially, and so we're more or less perhaps maybe not all in the double layer, but no, very close to the electrode surface. And we think that this change then is something associated with perturbations of the species close to the electrode surface. It could be that we have very little water around very close to the electrode surface, that most of it is associated with the absorption of the ions that we have there, in particular the anion, but also some of the cations that we have there, together with the electrolyte itself, and then that perturbs, for example, the species that we've got there close. And we wouldn't have seen that without doing this modulation excitation with the phase resolution. And so what we've been able to show is that the modulation excitation, for the first time, has been able to filter out the contribution from all the spectator species, and only give you those changes in the response of with the frequency to the species that are changing. Now, it's a very simple system. It's an ion 2, ion 3, but we can use this then to look at other systems as well. And I'll show you in a second a very exciting part associated with neutron scattering in a second. We're looking at why this is, but we feel that we're seeing some big changes in the hydration sphere around the ion cyanide, the ion ferricyanide system. It also gives us an opportunity to look at more liquid phase reactions. This modulation excitation has been used a lot in the gas phase with XAFs, but never has it been used in the liquid phase. And so this gives you a real opportunity to look at real systems operating under reaction conditions. We've also done this with neutron scattering, so total neutron scattering, and here the sensitivity issue is even worse. We have you have to normally under conventional conditions you have to have 2 to 3 atom percent changes to be able to see any changes in the neutron scattering pattern at all as well. So it's a very insensitive technique in that sense. However, we've done the same thing using the ion ferricyanide, 30 millimolar in KCl dissolved in D2O under neutron scattering conditions. Time resolved spectra doesn't show anything. The phase resolved spectra, however, does show significant changes. So this has improved our sensitivity close to 1 million times of the neutron scattering. It's very exciting. It allows us to look at changes in solvation sphere. It allows us to look at the solvent and the reactant. So XAFs looks at things that are heavy, like metals. The neutron scattering will look at things that are light, like the reactants, the products, and the solvent. And so we can get a full picture of what is happening around that active site under reaction conditions. Just like to say thank you very much indeed for inviting me to give this webinar. I hope the internet has held up. I'd just like to make some acknowledgements now, in particular on the CO2 work. Rebecca Taylor and Adam Greer did a lot of this work, but also the interaction that we had with Claudia's group and Miguel in particular was vital to what we were doing. So thank you very much to everyone involved in that. For the modulation excitation, My poor student Armando has had to put up with my stupid ideas about how we might be able to do this, but has done a tremendous job in extracting that data and getting it to work. Daniel Barron and Sofia Diaz Moreno have been the beamline scientists that have been associated with the work and are co-supervising Armando there. Daniel's at ICIS at the neutron source, and Sophia's at the diamond light source. And we've obviously had a lot of help from technical staff and other beamline scientists within Diamond, for example. And so I'd like to thank them, as well as our funding from EPSRC, the Catalysis Lab, and Diamond and ICIS. So thank you very much indeed for listening, and I'm happy to answer any questions that you may have.
Yeah, thank you so much, Professor Christopher, for your very nice presentation and for sharing some of your results with us this morning. Thank you so much. We do have some questions here, and the first one comes from Albert Bittencourt. Thanks, Albert, for your question. He acknowledges your presentation, and his question is, could you kindly explain how scalable ionic liquid absorption is in comparison to traditional PSA, TSA processes, please?
So we haven't scaled it up to any great extent. We have done things on a relatively large scale, using 500 mils of liquid. However, other people, in particular, Rich Nobel in the United States, have looked at larger scale activities, and so it is scalable. It's just a liquid adsorption with a pressure swing or a temperature swing desorption process. It's only then determined by the amount of ionic liquid that you have there and the price of it, I suppose. One of the issues with the ionic liquid, because they're a bit more viscous, is the bubble size that you get there. The bubbles tend to be rather large. So what we have done is we've done some oscillation frequency type activities where we can reduce down the bubble size significantly. That increases the contact area and therefore the adsorption kinetics, and that's been pretty effective. You can also use films of ionic liquid on surfaces to increase that interaction between the gas and the liquids, and that also provides us with an opportunity to do scale up work as well. These ionic liquids have been used in these types of processes at large scale, though. In fact, Eastman Chemicals had a process that worked from about 1980 to the early 2000s using ionic liquids on a very large scale, ton scale. So you can use these things, but they haven't been applied for CO2 at scale. They have been applied in this way for mercury adsorption, though. In particular, Petronas have a mercury adsorbent that is being used commercially using ionic liquids at scale.
Okay, thank you. We have another question here from Leonardo Siqueira. Thank you, Leonardo, for sending us your question. He also acknowledged your presentation. Physical absorption of CO2 by ionic liquids with permanent porosity is as efficient as chemical absorption by ionic liquids?
So, okay, so there has been some work using permanent porosity of ionic liquids with CO2. You do get quite a lot of CO2 in those. What you don't get is the CO2. It depends on whether you want to just get capture or whether you want to utilize that CO2. If it's just capture, then you can get a lot of CO2 in those ionic liquids, but it will desorb fairly straightforwardly, much more easily than the chemical adsorption. If you do want a conversion of the CO2, though, the ionic liquids which chemically bind the CO2 will then activate that CO2 that you can then do a electrochemical conversion, whereas you don't get that same effect or as much of that same effect with the physical absorption.
Okay, thank you. Now Viviane Ocampo Restrepo. Thank you, Viviane, for the question. So her question is regarding part 1. So before CO2 absorption, the Benz part has a charge localization on one of the nitrogen which could explain the CO2 preference at that site. So how is this charge redistributed after the CO2 absorption? And two, how this new distribution changes the ionic liquid properties? Sorry.
Okay, good question.
2 questions in one.
I don't know the answer to the first question, but of course it will change because the CO2, you do get charged then on the CO2 itself because it becomes CO2 minus at the but it's delocalized still, so you will get more spreading out of that charge. I can't describe it in any more quantitative terms. I'd have to go back to the calculations to do that, but of course you do get that increased amount of distribution. That new distribution of the charges, of course, will change the viscosity. What we see, though, is we see a small change in the viscosity. Quite often that viscosity will go up slightly. You get more binding of the CO2 with the cation of the ionic liquid, for example, because the charge is a bit more distributed. And also you have more accessibility, we think, to the CH2s around the phosphorus. You get quite strong binding of that. So you get a slight increase in the viscosity. It's nowhere near the same as what you get with the amino acid-based ionic liquids, which they go up by 10, 15 times in terms of their viscosity. We only get a small percentage increase in our viscosity. We don't really change too much the density, for example. We haven't looked so much at some of the other properties like heat capacity and so on, but the viscosity does go up a little bit.
Okay, thank you. Does our audience has any other questions? But it doesn't. So, Professor Christopher, I was quite curious about your expectations for the future as the scientific community adopts more of the in situ techniques to study catalysis processes, right? I do believe that the CO2 uptake, for example, can be improved a lot. What are some of your expectations? Since we have just written a review about in situ techniques and operando techniques applied to perovskite photovoltaics, right? And it seems in catalysis they can do a very nice job as well.
Yeah. So I'd say a lot of our work to date has been how we can improve our sensitivity and our time resolution. Many of the systems that we look at, as I've said earlier on, are gas phase systems because we don't have a lot of the solvent around the place. Using transient methods gives us an opportunity to really probe the active site with a solvent being present. So for example, we've done some work, as of others, where you use short time on stream. So you absorb. You only look at the very first sets of absorption because they're the strongest. You're not absorbing on other sites like the rest of the support. For example, if you have a metal nanoparticle on a support. And so by probing those short time on stream, you can really look at the active sites. We can use things like Sitka type experiments, so steady state isotope transient kinetic analysis, to again probe the number of active sites. That has not been used. Sitka has hardly been used ever in liquid phase reactions. It's been used a lot in gas phase reactions. It requires you to have a mass spectrometer that can monitor things very straightforwardly. So getting the analytical techniques that can monitor things at the right time scales with the right sensitivity is absolutely critical, as well as that link between the stimulation that you have there and the monitoring. I think we can do this. Modulation excitation, I think, has a real part to play, and you can use it for any spectroscopic or structural technique. So you can use it with NMR, you can use it with EXAFs, you can use it with infrared, Raman, whatever it might be, and it improves your sensitivity. And so I really feel that it's a good technique to be able to apply to many systems. It's not easy. Okay, it's not a very straightforward thing to do. You need phase sensitive detection and so on. But if you can get it right, it really is very powerful. But it is a combination of techniques that gives us the answers. It's not one single technique. The EXAFs, for example, gives us a lot of information around coordination spheres around the metal site, because it tells us nothing about the solvent or the reactants or what they're doing, whereas neutron scattering tells us nothing about the metal, but it tells us everything about everything else. So you can't use one technique, but that correlation between techniques and adding up all the various bits of information, getting the timescales right, I think gives us a valuable toolkit, and it's what we need to be able to do.
Yeah.
However, you always have to remember that, you know, there's a famous saying about, if you can see it change, it's not important in catalysis, because everything is much quicker. So understanding the changes that you're seeing, being skeptical about what it really means, and correlating the experiment with theory to try and say, is that species that we're seeing, that is that important? Does the theory back up that that's important as an intermediate, an active site, whatever it might be? I think it's that combination of things that we really need to focus on.
Yeah, thank you so much. So if you do have some other questions, please don't forget to send us to our email, and then the lecturer can answer them later on. So Professor Christopher, we hope you have a very nice day here in Brazil. Thank you so much for joining us and for sharing some of your knowledge with us, right? Thank you so much.
Thank you very much indeed.
Thank you. And for our audience, don't forget that next week we're going to have another webinar. So please don't forget to subscribe to our YouTube channel, CINE Energy, and hit the notification button so you don't miss the event next week and our next events inside this month yet, right? So thank you so much, Professor, again, and hope to see you soon. Thank you.
Thank you very much.
Also from our loyal audience, hope to see you next week. Thank you.
Goodbye.
Bye-bye.